So let's design an e-commerce product listing page. A product listing page is simple, where a small shop owner, say a small shop owner has 100 items to place. That 100 items are listed on a website. That's it. It's not a huge website. We start small. It's a really small website with at max 100 items that a shop owner needs to list. And now there would be hundreds and thousands of people visiting it, right? Now, what we want to do is we want to design the system. So whenever we approach any system in general, every system design would have a motive. The motive of this system design is that we understand how a system is built and we understand how to take a structured approach into solving that problem. Instead of taking massive leaps, we would take small baby steps into understand how systems are built, right? In this one, we would keep things simple to understand different pieces of infrastructure and how it fits into the scheme of things, right? Okay, the features that we want from this is that the owner should be able to add a new product, update or delete an existing product, list all the products on the website, and customer should be able to access the catalog. It's not about making the payment. Payment is not part of the system, right? We are starting small, keeping things simple. Okay, so now let's start with storage, because storage seems pretty simple to start with. Given that we are only storing only 100 items in the table and it is only one shop that we are serving from this, which means the data is not huge. The data can easily fit into single node. That's a general statement. Let's do some estimation. We know that there are 100 items that are stored. For each item, let's say what we have is we store title, description, basic color and whatnot, right? Let's assume that payload is 1 kilobyte. That's still decent enough, 1 kilobyte. 1 kilobyte multiplied by 100 is 100 kilobyte of data. Easily, it can fit into a small database server. That's where we say that, hey, 100 rows of data can easily fit into a single node, right? Now, because we are picking now which database to pick. When data is this small, typically not like you can pick literally any database and it would not make a lot of difference. But given that we still see some structure, some user information maybe there, or in any case, we are just making a listing of catalog, right? So there's not much that we are doing, but we still have decent enough structure, title, description, colors, maybe few reviews here and there, right? Those sort of stuff. SQL DB would work just fine because data is not huge. It does not make sense to go for anything fancier over here, right? So our storage is now fixed to a relational database in which we have some schema, which we are listing all the catalog that we have, right? Okay. Now storage part is done. Now we want a way to access this data. So given that this would be accessible over the internet, we go for our favorite protocol, which is HTTP, because browsers understands it. Whatever client API you make a call to, like everyone understands HTTP. Every client browser device understands HTTP, right? So we start with a very simple HTTP based server that exposes a bunch of APIs to access the data, because that's what we would want to do. Now, what we do is no matter how many requests we get, because this is where we are listing the catalog, so we may still see a huge number of requests that one server might not be able to handle. So what we do is we have multiple servers. As soon as we have multiple API servers, we have to put them behind a load balancer, because load balancer would become the single point of entry that every single client talks to, and load balancer would balance the load between these servers. Now the load balancer would have a domain name so that everyone just talks to this one stuff. Let's say it's called api.mystore.com. It could be anything, but let me give this name, api.mystore.com, and behind which there are multiple API servers serving those endpoints, right? Okay. The architecture up until now is you have bunch of users talking to your load balancer, behind which there are multiple API servers talking to your database. A classic 3-tier architecture: user, compute, and storage, right? Okay. Now here in almost every single system design drawing, because load balancer is ubiquitous, load balancer is almost everywhere in every single system that we design, it's typically the best idea to not draw this component for everything, because it just makes things messy. So from now on, whenever we want to define this component or draw this component, we would typically represent it via this. It shows that there might be a there will be a load balancer and a bunch of API servers doing that part. So multiple instances of it behind a load balancer or something like that, right? Let's call that service a catalog backend service. This catalog backend service is the one that would be dealing with all the backend APIs that you expose over this database. The catalog database is the one where you are storing the entire data. So this becomes our catalog backend service and a catalog database. So this becomes a simplistic view of our architecture up until now, because drawing every time load balancer just makes things messy, far too many errors. We'll keep it simple because it's easier to understand, because it's implicit that when you have multiple servers and you'd want to talk to them, you would have a load balancer there, right? Okay. But now for an end user, like a customer for us who are accessing that shop, we would need a front end as well, right? We would not just be making JSON call to get the data, right? For an end user, we need front end because that's what our requirement is. We want customers to be able to quickly access the catalog. So which means customer needs to have a front end to do it. So customer will talk to front end will talk to back end will talk to database. A classic way of building application. So your end user, instead of talking to your backend server, now talks to your catalog front end makes API call to catalog backend makes database call to read and update, or rather to read the data, because it's just serving the catalog, right? Okay. The next part is you need shop owner to update the data, add new products, update the title, description of the product and whatnot. Now, how would your shop owner do that? Shop owner needs a separate interface, something like an admin interface to configure it, right? So what we do is we define a service, a front-end service called admin UI. The admin UI service's job would be to invoke the same APIs exposed by the backend, which makes calls to the database and updates and creates and deletes and what all operation it needs to do, admin operation, it does on this database. Now here, why did we take a call to create a separate admin service and a separate front-end service? Because at the end, this is also front-end, this is also front-end. One of the reasons, and to be honest, in an early stage startup, you typically have both of them at one place. But as you grow, you need more components to do it. The reason, one of the main reasons why you should think there should be a different admin UI is because admin UI might have a different way to represent those things. Your user facing code and admin code should not intertangle, because if they get tangled, bugs from one might affect others and whatnot. You wouldn't want to keep things separate, especially when it comes to superpower like admin. Although you would have all the checks to make and update the entries over here that only admin should be able to update in the DB, but you would still want to keep the front end totally different. Otherwise, it's easy to hack through the system, because you would have the code base of your admin thing, the front end code base of admin thing that which would have APIs to call to backend, the admin APIs listed there, easier for people to hack and manipulate and whatnot. So that is where it is better to make the admin interface separate and front end interface separate. Right? You may have a common backend system. That's not a problem. And in the common backend system, when we have there, for every API call, you need to check if the user has admin privileges or not. If yes, then update allowed. Otherwise, it's only read that you would do. Right? Okay. Now let's understand. Now that we have pretty decent architecture, you have a front-end service, a user-facing front-end service. You have a backend service. You have an admin UI. You have a catalog database. Now let's understand the load on each server or each component of this. So you may have hundreds and thousands of users trying to access the catalog. All of them makes calls to front-end service, because that's how your front-end is rendered. The calls coming to your front-end service because this front-end service has its own load balancer and a bunch of API servers. Everything is stateless. API servers can scale independently. So more load coming to this load balancer, the more API servers you add over here. So the load on this will be huge in worst case, but it is very much handleable because you just need to add more API servers to scale it independently. Problem solved? Correct. Now let's talk about the admin UI. Who will be the user of this admin UI? Shop owner. You are only hosting one shop over there. So given that you're only hosting one shop over there, even one server is more than enough for you to host the admin UI. Here I have drawn load balancers with multiple servers wrapped in this one simplistic view of service. But in reality, you may choose to have, you may want to have that setup, but even one server is good enough for you to handle it so long as it stays up, all good. But if you still want to go beyond and ensure fault tolerance and high availability, you would have a small load balancer behind which you would have one server. In case that goes down, another server automatically spins up by your auto scaling policy and would do that, right? So almost every single cloud gives you a way for auto scaling. It ensures, like for example, in AWS, you have something called as target group, which ensures that, hey, if you specify that my target group behind this load balancer, there should always be at least 5 servers. It would ensure as soon as the server goes down, it would automatically spin up one server up. This is what your cloud provider typically abstracts the complexities out for you. You would have something similar over here, that no matter what, there should always be one server behind this load balancer, the minimum number of servers that you need, right? Okay, so the load on this is too less, but still for high availability, we are putting a load balancer and one server behind it. So this is set up, this is set up. Now let's understand the load on the backend. Backend would have pretty decent load, right? Given that backend has a pretty decent load on it, now what would happen? We would need to scale backend. Now here the backend server also has a load balancer and bunch of API servers. Similar to other services, the auto scaling policy over here depends on the number of requests that are coming into this. That's what you would define in your auto scaling policies, right? So backend is scaled up, admin UI scaled up, front end scaled up. The only thing that remains is this catalog database. In case of this catalog database, what happens when you see huge amount of load? Now here, given that we are not talking about payment system at all, it's only about catalog listing, not payments at all, which means your end user traffic is read heavy, right? And I've deliberately added this sort of constraint so as to emphasize on read heavy traffic. Now, given over here, no end user is writing anything to the database, end user is only reading from the database, there might be a huge read traffic happening on this DB. So now what do? Which means that you don't want, like it could be possible that this one database is not able to handle the incoming read load happening on it. So what do? You create a read replica over here and allow and make changes in the backend that it forwards the read request to this and some read request to this also, right? So write request would anyway go to master, but read request can be distributed over these databases. Now you'd say, okay, oh, but I've heard that master only takes care of write request. That's not a rule, right? Given that the amount of writes on this database is only generated from admin, the writes would be minuscule. What are you writing? You are only updating title, description, adding new product. 100 item shop, not much. So writes are very infrequent. So again, why I'm taking this? I'm talking about this because I want to bust this myth where you say that, hey, master only takes care of writes. No, that's not a rule that master only takes care of writes. Even master can take care of reads so long as it fits your system. In this case, it very well does. So here, the master will also take care of reads and replica would only take care of reads. Master will take care of reads and writes because the frequency of writes is not much. That is why we are keeping things really simple over here and have writes or have reads go over here, reads go over here and writes also go over here. Let me just quickly make that change and also add read over here. So the master takes care of both reads and writes. Replica also takes care of reads and writes. So now, how would you move read traffic or how would you make your read go to replica as well? Again, as I said in previous videos, that in the backend server, every API server that you start, you create two database connections, one to master DB, one to replica DB. Whenever you are reading from the database, you pick either this connection string or this connection string. At random you can pick. So read requests are going randomly either on this server or on this server, right? This way you would be able to handle your read load. Let's say your read load goes even further than what two servers can handle. You add one more read replica over here. If it goes beyond that, you add one more read replica over here. No one's stopping you from doing that, right? So we saw how we can scale reads independently, right? But given that the writes are very infrequent, coming only from the admin, it's okay. One server will handle it and then it will be replicated across all the databases, right? Okay. This is a very simplistic view of it. One key thing that I again want to reiterate that it is not a hard and fast rule that masters cannot handle read requests. It's up to you, your system, your logic that you write in the backend code. If you want to move read, like if you want master to serve some read request or not, you use that connection object and fire the request. As simple as that, right? There is no hard and fast rule that master should only take care of writes or not reads, right? That's not how real world works, right? Okay, now you would have spotted something. You would have spotted it. If I'm getting large amount of reads, can I not add cache over here? You very well can. There is nothing wrong in adding cache. But what I choose to do over here is I went with multiple read replica setup because caching is a common way to do things out. But here what I'm doing is I'm going with read replica. Why? Because now whenever master writes, or rather not master, whenever shop owner writes via admin UI, the writes happen on the master database, it would be immediately replicated to all the databases out there. If I would have added a cache, then I would have to consider cache invalidation, because now cache must be having some data which is serving to the end user. The data got changed. I would have to update the cache and delete that key. Instead of going that route, I chose to go with multiple read replicas, because at the end what matters is that we are able to scale the reads, and with multiple read replicas in picture, we are easily being able to scale the reads. Right? Now through this you would have observed how I picked up a particular problem and tried to make conscious design decisions at every single stage. Right? I had justification for every single design decision I made. In this case, like I gave you two options to scale it. I did it with read replicas. You could also do it with cache, right? But the way I did it is I could add more read replicas if needed. Given the write requests are very far and few, read replica setup is pretty much okay. You don't need cache complexities, because as soon as you add cache, you would have to think of cache invalidation. Here in this approach, there is no need of cache invalidation, because writes on master will be propagated to all the replicas automatically. Right? I went on that route. You could also add cache if you wanted to, but just because cache exists does not mean you add it. I went through this route. You could add cache as well. There is nothing wrong in it. Just need to take care of invalidation, right? Okay. So as part of this thing, this is what I wanted to cover as part of this very simple day zero of system design on how we are approaching a particular problem in a structured way. Now, what I want you all to do as part of this exercise, build this system. First of all, do a DB design. Do a DB design for the system. Just design a simple catalog. Define a proper structure, title, description, color, some information about catalog. Stuff it with 100 randomly generated data. Write a simple backend API server and expose those APIs. Now, set up a DB replication. Right? Now, in your APIs, now that you have set up a read replication, you have two databases. Now in your backend API, have two DB connections, one to master, one to replica, and alternate between the two. Choose one at random, alternate between the two. Pick an approach to move read requests between these two. Right? That some read requests go to master, some read requests go to replica. Right? Have fun with it. And then make just one change in master database and see how it propagates to replica. Right? Then you would see automatically you don't have to worry about cache invalidation at all. And that's the beauty of this design. Right? And also as a stretch, try to add cache into this architecture and in your implementation rather. When you do that, then you suddenly realize the problem of cache invalidation. As soon as you realize the problem of cache invalidation, you think, now whenever update happens, I have to invalidate the cache. Now you don't need to, because you have read replica setup. This is what I wanted all of you to experience. Right? So yeah, this is all what I wanted to cover as part of this really simple e-commerce product listing page. I hope it would make sense in a complete picture. It paints a very nice picture on how we make those design decisions, how we go about it, where we use this simple mathematics to give answers to these questions. Right? Okay, super. That's all what I wanted to cover in this one. I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks, Atar.